Hey, what's up YouTube? In this video we're going to continue looking at linear systems, and we're going to work towards finding a general method for obtaining the solution set of a given linear system. So one of the big questions in linear algebra is if a given linear system is consistent. Remember that a system is consistent if it has at least one solution, and using the theorem that we proved last time, that means that it has either one solution or infinitely many solutions. Now, if the system is consistent, meaning that it has at least one solution, another question linear algebra seeks to solve is if the solution is unique. We can answer these questions if we know the solution set of the linear system. So our goal here is to find a general method for obtaining the solution set of an arbitrary linear system. So we want to find a method that works for any linear system, so a general method that can work on any linear system that we're given. Now, I'm not going to be showing the general method in this video. We're going to be working towards it, so that'll be coming up in the next videos. But in this video, we're going to look at some preliminary notions that will lead up to that. So basically, the idea is that if we're given a linear system of equations, we want to replace that system with another system that has the same solution set, but that's easier to solve. So the key is finding operations that we can apply to a linear system that results in a different linear system that has the same solution set. We have three basic operations that can be applied to a linear system. So applying any one of the following operations to a given linear system results in an equivalent linear system. And by an equivalent linear system, we just mean a linear system that has the same solution set. So the first operation we can apply to a given linear system is we can interchange two equations in the system. So for example, if this is the system we started off with, we can interchange any two equations in the system. So for example, we can interchange the first and the third equations, so we'll just switch them. And we get this new system where now this equation is the first equation of this new system, and the first equation of the previous system is now the third equation of our new system. And doing this doesn't change the solution set. So everything that's a solution here is a solution in this system, and everything that is a solution of this system must be a solution of this system. Now the second operation that we can apply to a linear system is we can multiply all the terms of one equation by a non-zero constant. So for example, if this is our original system that we're given, we can multiply the first equation of this system by the non-zero constant 1/2. So we're just going to multiply every term in the first equation by 1/2. So we would get 1 times x sub 1 minus 1 times x sub 2 plus 3/2 x sub 3 minus 1/2. And now this gives us our new linear system. And again, this didn't change the solution set. Now finally, our third operation that we can apply to a linear system is that we can replace one equation by the sum of itself and a multiple of another equation in the system. So let's look at an example. Let's say that this is our given linear system. What we're going to do is we're going to replace the second equation of this system by the sum of itself and 2 times the first equation. So we're going to multiply the first equation by 2 and then add it to equation 2. And that will give us our new equation 2 for our new system of linear equations. So if we multiply the first one by 2, we'll get the first coefficient being 4, the next one being -4, and the third one being 6. And then the constant on the right becomes -2. Now we can add that to the second equation. And so these terms cancel out. -4 plus 3 is just -1 for the x2 term. 6 minus 7 is just -1, and that's for the x sub 3 term. And then of course -2 plus 6 is 4. So we get this new equation here, which will be the second equation of our new system. So our new system will have the first and third equations unchanged, so it'll keep these two equations, and then instead of having the second equation given here, we're going to replace it with this new equation. So our new system looks like this, where of course the first and third are the same, and then the second one is the equation we have from down here. So we have these two systems, and by what we stated above, these two systems have the same solution set. Remember, we said that they were equivalent, meaning that they have the same solution set. Now let's go ahead and actually prove this statement that I gave above. So we're going to prove that applying any one of the following three operations given here to a linear system results in an equivalent linear system, meaning it results in a new linear system that has the same solution set. So first, suppose that S is an arbitrary linear system represented by the linear equations given here. Now if we interchange any two equations of the system S, it's pretty clear we're not changing the solution set, because switching any two equations in the system doesn't affect the solution set. Similarly, multiplying all the terms of one equation in the system by a non-zero constant isn't going to change the solution set. The only one we really need to worry about is the third one. So we're just going to prove that if we replace one equation by the sum of itself and a multiple of another equation in the system, that we get a new system with the same solution set. So let S prime be the new linear system obtained from S by replacing the ith equation of S with the sum of itself and a multiple of the jth equation of S. So we get this new linear system S prime, where every equation of S prime is the same as its equation in S except for the ith equation of S prime. So the ith equation of S prime is the only equation in the system that's different from the system S. Now we said that the ith equation of S prime was the sum of the ith equation of S and a multiple of the jth equation of S. So we take the left-hand side of the ith equation, which is given here, and then we add that to the left-hand side of the jth equation, which is given here, multiplied by some constant c, and then we set that equal to the right-hand side of the ith equation, which is given by b sub I, and we add that to the right-hand side of the jth equation, which is given by b sub j, multiplied by the same constant c. The resulting linear equation is the ith linear equation of the new system S prime. Now if we combine the terms for each of the unknown variables, we get this representation of the left-hand side of the ith equation of S prime, where the coefficient for the x sub 1 term is given here, the coefficient for the x sub 2 term is this, all the way up to the coefficient for the x sub n term given here, and then the constants given on the right remain the same. It's just the b sub I plus c times b sub j. Now we need to show that the solution set of S is the same as the solution set of S prime. So going in one direction, let's assume that this n tuple with the elements y sub 1, y sub 2, all the way up to y sub n is the solution of the first system S. And we're going to prove that it must also be a solution of the second system S prime. So if we have this solution of the first system S, then this n tuple must be a solution of every equation in the system S. So then in particular, it must be a solution of the ith equation of S and the jth equation of S, meaning that when we plug in this n tuple to the ith equation and the jth equation, both of those equations are true. So that tells us that if we sum these up, where each one of these coefficients is the coefficients for the ith equation, then that will equal the constant b sub I. And similarly for the jth equation, if we take this sum on the left-hand side, where these are all the coefficients for the jth equation, so if we sum that up, we're going to get the constant on the right-hand side, which is equal to b sub j. So that's just from the fact that this n tuple is a solution of the system S. Now using that, we're going to add the left-hand side of the ith equation to the left-hand side of the jth equation multiplied by this constant c. And what we'll get is that this is equal to b sub I plus c times b sub j. The b sub I comes from this part, since we said that this is equal to b sub I, and then we also said that this is equal to b sub j, so this is where we get c times b sub j. Now since this is just the ith equation of S prime, this tells us that this n tuple must be a solution of the ith equation of S prime. Now since the ith equation of S prime is the only equation that changed from S, we know that this n tuple must also be a solution for the system S prime. Now for the opposite direction, we can assume that this n tuple given by v sub 1, v sub 2 up to v sub n is a solution of the system S prime. And now we're going to show that just given the fact that it's a solution of S prime, that it must also be a solution of S. The fact that this is a solution of S prime means that it's a solution for every linear equation of S prime. So in particular, it must be a solution of the jth equation of S prime, which remember is equal to the jth equation of S. So that tells us that this sum here, where these are the coefficients for the jth equation of S prime, is equal to B sub j. And we also have that this n tuple here is a solution of the ith equation of S prime, where the ith equation of S prime is given by this equation here. So when we plug the elements of our n tuple into the left-hand side of the ith equation, it will look like this, and we'll get that the right-hand side of that will equal b sub I plus c times b sub j. Now we can rearrange the left-hand side of this equation to make it look like this, and by doing that, it's made clear that this part is the left-hand side of the jth equation of S prime with our n tuple plugged in for the unknown variables. So this sum of everything within the brackets, this will be equal to b sub j, so that this whole thing will be equal to c times b sub j. So we have the sum of this plus c times b sub j is equal to b sub I plus c times b sub j. And so we can subtract this c times b sub j from both sides. So that leaves us with this part of the left-hand side equaling b sub I. So we get this equation. Notice that the left-hand side of this equation is just the left-hand side of the ith equation of our original system S, with the elements of our n tuple, v sub 1, v sub 2 up to v sub n, replacing the unknown variables. So they're replacing the x sub 1, x sub 2 up to x sub n. And then the right-hand side of this equation is just the right-hand side of the ith equation of S. So that tells us that this n tuple, v sub 1, v sub 2 all the way up to v sub n, is a solution of the ith equation of S. Now, since the only difference between these two systems was the ith equation, we conclude that this n tuple must be a solution of the system S. And that completes our proof. Now remember that our original goal was to find a general method for obtaining the solution set of a linear system, and we were going to do that by replacing the linear system with a new system that was easier to solve. Now what we just proved was that any one of the three basic operations above can be applied to a linear system to get a new system with the same solution set. So these three basic operations are the main tools that we're going to use to solve linear systems. So I'm going to stop the video here. Thanks for watching, and I'll see you next time.